Yeah, thank you, Natalie. And yeah, of course, yeah, thanks for the invite. And like I was just saying before, yeah, I think this is a great idea to have, and for me to kind of advertise our recent paper and the work that I've been doing as part of the LEGO project. So yeah, my talk will focus on this project, LEGO, which is a project aimed at focuses on studying molecular line emission as a tool in the Milky Way, as a tool to study extragalactic observations. And this started out as a IRAM 30-meter large project, so covering various regions in the galaxy. I think we have a sample of around 20 plus large maps of typical 3mm lines of various star-forming regions throughout the Milky Way, both kind of towards the galactic center, so kind of quite low galactic longitudes, out to quite high galactic longitudes towards the outskirts of our galaxy, to really get the range of environments through our galaxy and really understand molecular line emission, and and allow us to use that as a tool for then studying extragalactic observations. And now we've started to progress into the kind of 1mm window with the kind of publication of our recent paper. So I'll briefly touch on that, but still very preliminary results there. So if we have time, maybe I'll just show a few maps there. So then, here's the kind of overview abstract of the paper. So please feel free to click on the link here and read that in your own time. Quite a long paper, as it's kind of the first paper from the large survey, and we had to kind of explain the various observing and data reduction processes throughout the paper, but some interesting science towards the end, which I'll be touching on today. So then, just to kind of present a very basic picture as to why we're doing what we're doing, and a kind of very simplistic picture of star formation and molecular line emission. So then here's a picture, a very much a toy model picture of star formation throughout a kind of typical GMC within our galaxy or an extragalactic system. So then we have the formation of molecular clouds, giant molecular clouds, and then molecular clouds, which are kind of reasonably dense structures, which then go on to collapse and cool and form denser, more compact regions within them. And then eventually you get star formation, which then heats the gas, destroys, evaporates the clouds, and in the process heating and reducing the density of that cloud as well. So this is a very simplistic picture, of course, of star formation here. And in the picture of kind of molecular line emission, what does this mean? So again, a very simplistic plot here. So as a function of time, which is kind of just removed off the x-axis here, you'll see in the next slide, the bottom here, but we have time on the x-axis, and then here is like density and temperature. So if you go from this kind of picture of 1, 2, 3, so molecular cloud dense to star forming, we have these various stages kind of labeled here. Again, a very simplistic picture, but we have an increasing density as your molecular cloud would collapse, and then you have this increase in temperature. And what does that mean for the molecular line emission? So then you would expect species such as CO to kind of form, be quite abundant, and therefore, and because of its low critical density, emit within this low density regime. And as the cloud collapses and cools, you get a mix of chemistry and excitation with the higher density, and other molecules such as HCN, potentially N2H+, become interesting for chasing this then denser gas phase of the ISM. And then when you get the star formation, the temperature rises, these molecules get destroyed, and you don't get emission from these molecules. So then just to touch on this, this is a very important kind of large picture to understand, and various effects kind of wrapped into this, because now we're really starting to kind of probe the scales, not just in our own galaxy, which we have been doing for quite some time now, but in extragalactic systems as well. So here is just a kind of overview of one galaxy, so NGC 3627. So a very nice map of the CO2 to 1 emission here. sorry, wrongly labeled at the top. This is from the FANG survey. And then we've got kind of, this is the molecular gas, so that very first stage of star formation. And then we've got our intervening kind of molecular gas, dense molecular gas phase, which is the HCN. And then we've got the star formation coming later, here traced by the H alpha. So the kind of key here is to understand kind of the various stages of this molecular line, this various stages of star formation, and the links to molecular line emission to really get at the kind of physical properties of these extragalactic systems with the molecular line emission. Okay, so there's a very basic picture, obviously there, but I think that quite nicely sets the scene as to what we're doing. So then, we focused for this first paper on the W49 star forming region. So it's a very famous high mass star forming region located on the far side of the galactic disk, so around 11 kiloparsecs, so quite far away. But the benefit of being so far away is that we can cover quite a larger area, kind of projected scale on the sky, with, well, I guess a large map, but a relatively kind of reasonable size map. So kind of a 1 square degree by 1 square degree here is around 100 parsec by 100 parsec region on the sky. And this is what we focused on here. So this top panel presents a very nice kind of 3-color image of the galactic plane, and this black region is the region that we studied. And the region that we studied, as I said, is kind of 100 parsec by 100 parsec, and includes a lot of interesting features, such as the massive star forming region, W49A, but as well various supernova remnant here, W49b, and various kind of cold clumps and various other features around the map here. And then, so then we have our LEGO observations, which I'll come to in just a second. So this is including 12CO, which I show here. But then we also have access to Herschel observations, which we can use to fit the SED and get the column density of the molecular gas and the temperature of, well, the dust temperature there. So then coming to our molecular line observations here. So I don't want to go kind of too much here, a lot of information, but so here's some nice spectra on the left-hand side. But then this table really shows our molecular line catalog in full here. So this is a little bit small on the screen. You can see in the slides I put in the chat. But this is a really nice table from the paper. So you can see it nicely summarizes the various molecular lines across that kind of 3 millimeter window, and the frequencies, the energy levels of those molecular lines. But also quite nicely, it summarizes the critical density of these lines. So here, we just kind of zoom in a little bit. We have our kind of 2-level critical density, which we outline here. So this is the kind of typically quoted critical density that you would see in papers, just because it's the easiest one to calculate. And then you've got the full critical density, which accounts for all the level transitions. And in doing so, you've got the collisional rates, which then you account for. You kind of sum all these collisional rates together, similar to what, I guess, kind of, for example, Yancey Shirley's paper went into quite a nice detail of a few of these lines here. And now we really do this for a selection of lines across this 3 millimeter window. So I think this is really nice kind of database to look at here in your own time. And then we also give the effective critical density. So this is again taken from kind of Neil Evans and Yancey Shirley's work. So this is an effective critical density, basically a more physically, observationally, motivated way of outlining this critical density. So you can see here, just looking at these critical densities, I mean, people usually employ these to say, for example, HCN 1 to 0, it has a critical density of around 10 to the 6 per cubic centimeter. Therefore, it's tracing gas at that critical density, so 10 to the 6. But then in reality, we see by just accounting for more level transitions that are possible and doing the full calculation, it already decreases by almost an order of magnitude here. So this is kind of the first kind of alarm bell indicator that, you know, these broad statements that people throw around in the literature, we have to be kind of careful just from kind of simple calculation that you know, these could be order of magnitudes kind of in this already. So yeah, so this is a nice resource, I think, to look at for these molecular lines. Okay, so then going to molecular line observations of our W49 source. So here we plot the column density, so just the kind of summed material along the line of sight. So this is kind of just how much stuff you have. Obviously, the dust temperature. Both of these are very important for excitation chemistry. And then we have our moment maps for the various molecular lines, plotted in a very simplistic way here. So then we order the moment maps here by increasing critical density. So we go from our CO lines to the right. So these have a critical density around 10 to the 3. And then we have our more complex molecules, and these kind of go up from around 10 to the 4. So then you've got something like N2H plus going up to HCN, which would appear to have the highest critical density here on the right hand side. So I mean, just by looking at this in a very kind of simple way, you can see here that going from right to left, okay, for the CO lines, this is fine. But then you get to more complex molecules, and something like HCN seems to be more extended than potentially the N2H plus, which is somewhat counterintuitive because we've just said that, I don't know, this kind of broad statement that I sometimes see in the literature that HCN has a critical density of X, its tracing density of X. N2H plus has a critical density of Y, its tracing density of Y. But then that obviously doesn't seem like the fact here, because the HCN is more compact and appears to be tracing these higher density kind of structures that we're seeing in the column density map here. So there's obviously, I mean, very simply, other things that are influencing it. It's not just an excitation effect, which is ultimately what the critical density is telling you, purely excitation. There's abundance, there's opacity in here that are all driving the brightnesses and what these lines are essentially tracing. This is something that's kind of very crucial, very simple, and I think within the literature you see these statements, and I think that it's important to consider this. Okay, so then we can kind of slightly be more quantitative about this, and here we determine this so-called kind of emission efficiency. So this is kind of how bright the line is, your line, so your CO line or your HCN line is per H2 molecule. So basically you just take your line brightness, divide it by the column density. So then this basically shows you, so then if you have a very high value of your emission efficiency, then you would, your line would be emitting very efficiently within that region, but at a very low value, then it would be emitting very less efficiency. So this was studied and outlined by these various papers from Jens Kaufmann, Jerome Petty, had a few papers 2018 and 2017, I believe. So a few years ago, and they outlined this as a quite a useful tool to study these various molecular line emission regions. So for example, of Orion, obviously the simplest region, the closest region, so kind of a very different region to what we're studying W49 in terms of star formation. But just to show here, they see that this 12CO has a very high emission efficiency at the lower column density end, so kind of or low extinction as well, say. And then within moderate ranges, you get molecules such as HCN start to emit. So you can see, I mean, in the previous slide, you saw that the HCN was quite extended, showing that for the kind of moderate kind of column density regime, that's obviously very bright, emitting quite brightly, efficiently, sorry. But then going to higher column densities still, you get molecules such as N2H+, which have been known for quite some time to be particularly good tracers of the high kind of dense gas column density range. And you see that these molecules then on the high end emit efficiently. So this is quite a nice picture here, showing that going from the CO to the HCN and the N2H+ are tracing kind of fundamentally different regimes in terms of densities throughout our molecular cloud, which isn't always intrinsically linked to that critical density. Okay, so now we plot W49, and this is the picture we get. So again, going from kind of column density on the x-axis and then emission efficiency on the y-axis, you can see a very different picture here. So for the CO lines, kind of relatively similar. We have a decreasing trend. They're peaking on the low column density end. But then, for example, for HCN or N2H+, you see that they actually peak at quite similar regimes, which is very interesting. But I mean, like I said, W49 is 11 kiloparsecs away. So on the other side of the galaxy, you have a lot of material in between you and it. It's kind of, these were probed by similar size, angular size beams. So then the physical linear size beam of W49 is significantly larger than Orion. And we're covering a significantly larger area than was done for Orion. So I mean, it's very interesting that they are different, but it's also very interesting that they're kind of even remotely the same, because you've got so much confusion towards W49. The star formation, the conditions are completely different. So it was really interesting that we even recovered these kind of trends to begin with. So then, yeah, back to the picture in W49, we see that the N2H plus the HCN is somewhat similar. So then kind of going back to our first kind of toy picture of line emission and cloud evolution, we plotted here the density, which is fundamentally kind of what we're showing here, just a kind of column density or density probe. But there's fundamentally another parameter, which is the temperature, which could be driving this, both the chemistry, the molecular line emission, the excitation as well. So then kind of the new analysis that we kind of employed for W49 was to try and split this up. So this wasn't really done in Orion, but now I think this is super cool that we can do this here. So then what we do, this is exactly the same as what I was showing before. So kind of where the contours peak is where you have that high emission efficiency. So where these molecules are kind of very efficiently emitting and what kind of region of this parameter space they're emitting most efficiently. So similar to kind of the peaks here or the peaks in the column density here. So again, we have the column density on the x-axis here and the dust temperature now on the y-axis. And you can see again that the CO here is on the kind of low end, and we have kind of shaded region here because we're not quite sure various uncertainties with the column density, particularly on the low end here. So this is why this is shaded, but nonetheless, we see that the CO is kind of peaking on that low end, as we saw before, C18O intermediate range. And yeah, if you were just looking at the one axis, you would see, okay, so then these two blobs would merge and you would see that they're tracing similar material. But now with this third dimension, second dimension, I guess, but these split up in terms of temperature. So for a single column density, you see that the HCN is emitting kind of within that high column density, but high temperature regime, whereas N2H plus appears to be split up and yes, it's emitting towards the high column density, high temperature, but there's also a peak more towards that low column, the high column density, but low temperature. And this is very much in line with what we'd expect kind of from the chemistry of the N2H plus. It's very kind of sensitive to, for cold environments, for its formation pathways. So this is a very kind of clear and nice picture, I think, that we present here for the kind of splitting of this emission within W49 in this kind of column density temperature space. And then lastly, we can kind of come to kind of making this, looking at this in a more kind of linking to the more physical parameters, so the density of the cloud. So here we plot, again, the column density on the x-axis, and here we just plot the cumulative distribution function of the line emission across the source for the different molecular lines. So then here we have the 12CO in blue, and then lines to focus on here, as we showed before, are N2H plus in green and the HCN in red. And you can see that a lot of the emission from the CO is coming, so the bulk, so 50% of the kind of total emission across the source for the CO is at relatively low column density, and then you're kind of pushing more to the high column densities here. And I should say this is just focusing on the kind of central position around W49 here. And then, so then that central position of W49, we can get an idea of kind of a very rough idea of the density structure within this region, just by, I think we just took the kind of projected area on the sky of each pixel, and then we just said the depth of the pixel is basically kind of the volume that we're interested in, and then what column density, what density does kind of that volume and the column density give us. This is how we determined our density here, which is then shown on the lower axis. So increasing column density, increasing density here. So it's a very simple probe of the density, nothing too complicated. And yeah, so like I said, so then the kind of 50% point of the CO, so where the bulk molecular emission is coming from, is this kind of density corresponding to around 10 to the 3 per centimeter cubed, approximately, which is kind of in line with what you'd expect from its critical density, which kind of going back to that table, which I showed before, was around this kind of 10 to the 2, 10 to the 3 centimeter cube. But then going to something like HCN or H plus, 50% of their emission is indeed at high column density, but that doesn't correspond to anything close to the density of their critical density. So kind of at this very simple density analysis, we see that they're coming from around a few times 10 to the 3 to 10 to the 4-ish. And that's not even close to their critical densities, which are around 10 to the 5, 10 to the 6, which is something that was also highlighted in Orion, that this may be the case. And this can become, again, various effects, such as the increased, you just have a lot of abundance of these molecules, or additional excitation effects. Electron excitation could play a role here, particularly for things such as HCN. So various effects may be causing this. That's something that we definitely want to look into in future. But then, like I said, just this first work was presenting these results. And I think it's really cool that we can even kind of pick out these trends similar to what we saw in Orion, kind of in this massive star forming source, which is a lot more complex and a lot more distant. So again, okay, so then that's kind of the main bulk results of kind of the 3 millimeter line survey. And I just want to highlight that this is very obviously interesting to you guys with the Argus. I've been kind of reading about just before this meeting, and I read the white paper for the Argus Plus or Argus 144 instrument. I think it's be really cool, obviously, but doing similar analysis to this, having such a large kind of multi-pixel capability is very beneficial for covering such large areas, and then covering this 3 millimeter window in various lines, such as here I show kind of a galactic example. You've got the 13 CO, the H and C here. So it's kind of similar lines to what we were looking at in our study, that can be done now with Argus, and of course in future, hopefully with the new Argus instrument. And then, here's an example again taken from the white paper of an extra galactic source. So then the kind of implications for what we learn for these galactic sources, potentially with the GBT, could be applied to then the extragalactic community. So a lot of interest there, and I'm sure a lot of links between what I've been doing and what I've presented, and potential for what is possible with the GBT. And just in the last few minutes, I'd just like to highlight kind of very first results here on the kind of the next step, I guess, with the LEGO survey, particularly for this source at least, and that's moving into the 1 millimeter window. So this is quite a nice focus, and again, comparable to Orion. So a lot of studies of Orion, particularly in the 1 millimeter window, kind of following up those initial results from Orion. And here's an example of one such spectra And then we have these new observations of Apex following up, covering a similar area in W49, but now with these higher J transitions, so kind of the 2-to-1 transitions for the CO and the 3-to-2 transitions for those high density tracing lines up on the high frequency end here. And yeah, we're going to really use these lines again to kind of study the distribution of these lines. Are these lines again tracing higher density regions within the source, but also to do some radiative transfer to really get at that density, the physical property that we're kind of really interested in across the source, which I was just showing, previously showed here. So we've got a lot of nice coverage here with Apex. I think we cover around 64 gigahertz of bandwidth of these lines. And the kind of very first results here, I just like to show is, so you've got the CO lines here, the 2-to-1 lines, and then the 3-to-2 lines for the other species. So yeah, I guess still very early stages here and very early data reduction. But yeah, I was working on this, sorry. I was working on this earlier this week, and yeah, I just wanted to show because I think these are very nice detections, and I think there's some interesting science we could do here. Yeah, following up on our results in the 3mm window, sorry. And yeah, that's all my slides.
Thank you, Ash. So do we have any questions?
Hi, Ashley. This is Pedro Salas. Thank you for the very nice talk. I have a question regarding these tracers and their comparison. So you've shown moment zero maps, I imagine, but I was wondering if from the kinematics of the lines, do you see any evidence that they might be tracing different volumes of gas?
That's a good question. Yes, we didn't look into the kinematics. We didn't go into too much detail with the kinematics yet. We were just looking at kind of that bulk distribution, just summing everything along the line of sight in a kind of similar comparison to what you would do, say, for an extragalactic observation. So this is really just kind of an analysis of, say, yeah, in a typical extragalactic observations, you get down to, I don't know, with ALMA, a few megaparsecs, you've got like 100 by 100 parsec pixel, there or thereabouts, or beam. And then here we've got kind of size of a region, 100 by 100 parsecs. So just summing everything up in that box and then kind of making a kind of direct comparison to what those extragalactic observations would see in a single beam to now what we can resolve here across this region of our galaxy. So that was kind of the experiment that we were aiming at here. So we didn't look into the kinematics too much, but that's something definitely that we're gonna look into in future. It's gonna be very complex. W49 is known for being a particularly complex source, not just in the kinematics, but also self-absorption features, particularly towards the center of W49 is known to be a problem. So yeah, I was kind of putting that on the back burner for now, and yeah, potentially getting a PhD student to work on such a project. I think would be very interesting though.
Hi, Ashley. This is Glenn. I had a question for you. You probably said this and I missed it, but with these single lines, you have to use a temperature input to get the abundance. So are you using what data are you using for the temperature? You're using some survey to get the temperatures to turn them into abundances, right?
Yeah, so we didn't. So we haven't used anything. We haven't done any modeling. We didn't do any radiative transfer. We were just taking the bulk kind of brightness of each line and not kind of commenting on the abundance in any way. That's something that we would need to do in future. Like I said, with these kind of with the combination of the 3mm and the 1mm, doing kind of radiative transfer, radix modeling would be something that we want to do to get at that density, and for that we're going to need the abundance. That's correct. In terms of the temperature, we were using the dust temperature from the Herschel SED fitting. So Herschel SED fitting, I think we went up to maybe even the 500 micron, so maybe like the 160 to 500 micron. which then gave us the disk temperature maps, the column density maps at around 30 arc seconds, which was nice, comparable to IRAM 3mm, which is also a beam size of around 30 arc seconds. This is what we use. But in terms of, so this is what we use to kind of for the comparison, but in terms of abundance, we haven't assumed anything to do with the kind of abundance of the molecules as of yet. This was just an analysis of the brightness of the lines and how that fits within this kind of observed parameter space.
Well, that's what your sort of efficiency parameter was really effectively, is how bright the lines are at that. I mean, given a temperature, I mean, that's what I guess I was really wondering exactly what you meant by efficiency. If you didn't mean that the lines are bright at some, these particular lines are bright at some temperatures and less bright at other temperatures when the transitions change. Is that what your efficiency parameter meant?
Yeah, so I guess I guess the efficiency parameter can be broken. So maybe it's a little bit simpler if I kind of bring it into this picture. It's basically just it could be linked to the abundance, the chemistry, and the excitation of the lines. It's most likely a mix of all of them, but it's very simply just taking the integrated line brightness, taking the kind of the total column density along the line of sight. So for each H2 molecule that you have, what's the corresponding contribution to the Kelvin kilometers a second of your line that you observe? So then, yes, there is going to be abundance effects in here, which would then affect this, with temperature, which is why we're kind of, which is why we broke it up into this kind of parameter space to look at here to try and understand this complex parameter space that we have.
Thanks.
So I mean, this is again, I just like to highlight that this, I think, was a really cool result that we saw this in the first place, and I think that kind of more in-depth studies too within the source as well, W49, but across the LEGO sample, and getting at kind of various questions to do with the chemistry and the abundance is definitely something that we kind of want to follow up on. And as I said, using these higher J transitions will definitely help with that as well.
Ash, so I had a question on the isotopologs. So I saw in your survey that you had several isotopologs of like HCN, HCO plus. So have you done any analysis to see how those vary in your plots that you showed on like slides 10 or 11? How you showed like their peak versus the column density.
So I didn't put in the paper in the slide, sorry, but if you go to the paper, these are all presented in a somewhat more kind of complex figure here, where we did do the kind of analysis, just presenting these for all the sources, for all the lines across the source. So here you can see how they vary. For example, if I can pick one out, these lower kind of this row, the H13CN and these, but these are kind of very low signal to noise lines as you'd expect from the isotopologues, and I suspect you're losing quite a bit of information in the lower density gas, and they're just peaking towards this kind of center of W49, which is then giving you this high emission peak up here. But again, a lot of information to take in from all of these lines, and as a very first pass, we focused on those these typically observed lines from extragalactic studies, the HCN, the CO, and now moving into the NTH+. This is obviously becoming of quite some interest now to those extragalactic community. But I mean, definitely this is something that we kind of looking at all of these lines in more detail is something that we definitely kind of have on the radar to do. But absolutely. Yeah, I think distilling this down to such a large data set with such a large lines, which is kind of the standard now for, kind of having a broad, kind of multiple lines within a single observation is a very complex problem to do. And there's a lot of possibilities to follow up on here, both in terms of kind of simple taking everything, looking at the distribution of various molecular lines and these kind of isotopologues, but then, as you said, looking at the kinematics in there as well is definitely of interest. I think we have something like, I mean, it's not crazy high spectral resolution, but something like 0.5 kilometers a second or so spectral resolution.
Mm-hmm.
So, I mean, reasonably low if you're kind of wanting to do any kind of in-depth kinematic analysis, but just looking at the broad distribution of kind of features within the map is definitely something that we have to do. And then this is without going into kind of doing the correlations between the lines themselves, which is a very useful tool for extragalactic observations, kind of looking at various line ratios as tools for kind of properties throughout the regions. So looking at things such as the CO to HCN ratio, or recently, I don't know if you're familiar with Alvaro Hakar's work, looking at kind of this potential temperature probe, the HCN over HNC ratio, and then you've got various other ratios tracing these dense gas ratios, and then you've got PDR tracing ratios, such as the HCO plus over HCN. So you've got this other kind of wealth of information obtainable from these observations that really haven't been tapped yet. And I'm really excited to kind of follow up on this, looking at those line ratios too, and to see what they can tell us about kind of the various conditions across the region. And this was something that was kind of, if you read Jerome Petty's paper on Orion, I think there's kind of a group of papers on that source just from that one data set. You'll see that this is quite a wealth of information, say, to process. So I think it's definitely something that's going to be worked on, but over the course of a few years with this data set for this one source alone. And then, as I said, the LEGO data set in whole is several sources distributed across the galaxy, where you've got the same set of observations. So a very significant data set and a lot of information to deal with here for this survey.
Thanks. Great. Any other questions for Ash?
This is David. Just a quick question. Just looking at this, I'm not sure if people have done this with galactic star forming regions. I know they do like age dating of activity in clouds, but just looking at this, have people looked at the N2H plus versus the HCO plus ratios, because HCO plus tends to be lit up basically with star formation, where the N2H plus can be bright without a lot of star formation, just a dense clump. I know people use other line tracers for that kind of stuff, but if we're going to extend it to extragalactic work, we wouldn't be able to see some of the more, the weaker lines that are used for age dating, like the deuterated species and stuff like that. I was just wondering if people have looked at specifically N2H plus versus HCO plus for that kind of analysis of regions.
I'm not entirely sure. Like I said, I think this has been done for Orion and definitely studied within Orion for our galaxy. And then for, as you said, for extragalactic observations, this is really pushing the signal to noise obtainable now. But I think there are studies for getting at the N2H plus in these extragalactic observations, kind of follow-ups to various studies such as Empire for one. So this is a large study, again, using the IRAM 30 meter to get these 3 millimeter lines, dense gas tracers. And I think there's various follow-ups now, with the NOEMA, ALMA, kind of pushing to those higher resolutions, getting rid of a lot of effects of beam filling problems that you run into with kind of a kiloparsec beam down to a few hundred parsecs to sub 100 parsecs. So I think kind of, yeah, using line ratios such as that, N2H plus over the H0 plus as potential kind of age tracers is something that on a extragalactic side is just coming into the forefront and just, I think, becoming of interest. And yeah, I think it's something that definitely we'll have to look into for galactic observations. Yeah, like I said, from the galactic side, I think this has been done in Orion. It's something that we definitely want to look at here, but we haven't yet. As I said, we're kind of line ratios are on the kind of up and coming, but yeah, I think this is something that could be looked into. And I guess this is something that the GBT can also probe with, this can also get the H0 plus and the N2H plus. Is that correct?
Yeah, we can do both of them, not simultaneously though, unfortunately. So the studies, generally what we do is they look at N2H plus with people looking at N2H plus or the HCO plus and HCN. Those could be done simultaneously. Thank you.
Thank you. That's a good point.
All right, any final questions for Ash? All right, we will wrap up here. We will not have science lunch next week due to Thanksgiving, but we will be back on December 3rd, and our speaker is Mike Chen from Alberta. All right, so we'll see you then.
All right, thank you, everybody.
Thank you.
We'll see you.